March 15, 1941, Vickers-Armstrongs facility in Brooklands, England. British aeronautical engineer Sir Barnes Wallis spreads blueprints across his drafting table. 10-ton earthquake bomb calculations cover every surface. The goal is revolutionary. Create underground explosions that shake fortress foundations like a 3.6 magnitude earthquake. Germany's concrete bunkers, 8 meters thick, stand impregnable against conventional bombs. But Wallis envisions something different, a weapon that penetrates deep underground before detonating, sending shockwaves through solid earth rather than dissipating through air. The steel-reinforced submarine pens at Saint-Nazaire mock Allied bombing attempts. Luftwaffe engineers calculate their concrete barriers can withstand any existing weapon. Wehrmacht commanders sleep soundly behind walls that conventional bombers cannot scratch. In the Pacific, Japanese military engineers carve networks of caves into volcanic rock on Iwo Jima, creating fortifications they believe impervious to Allied assault. Italian concrete fortifications line the Mediterranean coast, designed to repel any invasion force. The Axis powers have built what they consider invulnerable defensive positions. None of them know that, in a cluttered workshop in Surrey, Barnes Wallis is about to change the mathematics of destruction forever. The morning of May 17, 1943, Wing Commander Guy Gibson leads 19 modified Avro Lancaster bombers on Operation Chastise the Dambusters raid. Gibson's success with the bouncing bomb against German dams proves Wallis's earthquake theory works. But the dams are only the beginning. In his post-raid analysis, Wallis calculates that a 12,000-pound bomb, dropped from 18,000 feet and reaching 750 miles per hour, will penetrate 60 feet underground before exploding. The resulting camouflage underground cavern will collapse any structure above it, no matter how thick the concrete. The Air Ministry, initially skeptical, witnesses the Ruhr dams crumbling. Sir Wilfred Freeman at the Ministry of Aircraft Production immediately authorizes development of Wallis's earthquake bomb concept. The weapon receives the codename Tallboy bomb, medium capacity, 12,000 pounds. Unlike conventional bombs designed to maximize explosive content with thin casings, the Tallboy prioritizes penetration. This high-tensile steel shell, cast in a single piece, measures 4 inches thick at the nose. The aerodynamic shape, 21 feet long with a maximum diameter of 38 inches, spins as it falls, generating gyroscopic stability that maintains accuracy even as the bomb approaches supersonic speeds. At the Vickers River Don Works in Sheffield, workers pour molten Torpex explosive by hand into the upturned bomb casings. Torpex, 50% more powerful than TNT and enhanced with aluminum powder for extended blast duration, fills the weapon with 5,200 pounds of devastating force. A 1-inch layer of pure TNT tops the Torpex, followed by a 4-inch woodmeal wax composite seal containing 3 chemical time fuses. The entire cooling process requires 1 full month. Each Tallboy costs more than most houses. Crews receive strict orders to bring unused bombs home rather than jettison them into the sea. The first Tallboy leaves its rack on the night of June 8, 1944. Squadron leader Leonard Cheshire guides 19 Tallboy-equipped Lancasters of 617 Squadron toward the Saumur railway tunnel in France's Loire Valley. The tunnel carries the main north-south rail line. German panzer reinforcements must use this route to reach the Normandy beaches where Allied forces have landed 2 days earlier. Conventional bombs would merely crater the tracks, easily repaired within hours. But the Tallboy aims for something more permanent. Flying Officer Stuart Anning releases his Tallboy from 18,000 feet. 37 seconds later, the weapon strikes the hillside above the tunnel at 750 miles per hour. The hardened steel nose punches through solid rock as if it were mud. 60 feet underground, the delayed fuse triggers 5,200 pounds of Torpex. The explosion creates a cavern 100 feet wide and 80 feet deep. The tunnel roof, no longer supported, collapses in a cascade of limestone and debris. The railway line, Germany's critical supply artery to Normandy, remains blocked for the remainder of the war. In his command bunker outside Berlin, General Heinz Guderian receives the report with growing alarm. The Saumur tunnel destruction halts an entire panzer division's advance toward the Allied beachhead. For the first time, A single bomb has severed a strategic transportation link thought permanently protected by geography and engineering. Guderian immediately dispatches engineering teams to assess German bunker vulnerabilities. Their conclusions terrify the Wehrmacht High Command. If the British can destroy 60-foot deep tunnels with precision strikes, no fortification remains truly safe. The terror spreads through German defensive planning as Allied intelligence identifies the earthquake bomb's potential. Organization TOT, responsible for Atlantic wall construction, receives emergency orders to double concrete thickness specifications. The Regelbau standard build system, previously calling for 3.5-meter reinforced concrete on Class A installations, escalates to 8-meter minimums. Construction crews, already stretched thin across occupied Europe, divert from offensive projects to defensive reinforcement. Thousands of workers abandon V-weapon sites and submarine construction to pour concrete barriers the British earthquake bombs might penetrate. But the Tallboy has only begun its campaign of destruction. June 14, 1944, marks RAF Bomber Command's first major daylight raid since 1943. The target, E-boat pens at Le Havre, where German fast attack boats threaten Allied shipping in the English Channel. The pens hide behind concrete roofs 8 meters thick barriers that have deflected every conventional bomb dropped by previous raids. 22 Lancasters of 617 Squadron approach at 12,000 feet, each carrying a single Tallboy. The German E-boat crews watch from their concrete shelter, confident in their protection. The first Tallboy strikes dead center on the pen's roof. Unlike conventional bombs that explode on contact and spread their force outward, the earthquake bomb punches through 8 meters of reinforced concrete before detonating inside the structure. The explosion vaporizes everything within the pen boats, equipment, fuel stores, ammunition. The concrete roof, designed to protect against attack from above, becomes a tomb when the blast occurs inside its walls. German naval personnel, accustomed to riding out air raids in their concrete shelters, discover their fortress has become a death trap. Captain Zur C. Hermann Buchting, commander of the 5th E-boat flotilla, witnesses the attack from the harbor control tower. The explosion lifts the entire concrete roof 20 feet into the air before it crashes down in fragments. Buchting's radio crackles with desperate reports from surviving E-boat bases along the French coast. Le Havre, previously the flotilla's most secure harbor, lies in ruins after a single British bomber formation. Within hours, Buchting receives orders to evacuate all remaining E-boats to IJmuiden on the Dutch coast better protected, but farther from the invasion beaches where they could interfere with Allied operations. The psychological impact spreads faster than the physical destruction. German naval engineers had calculated that 8-meter concrete provided absolute protection against aerial attack. The Tallboy's success at Le Havre shatters that confidence. Admiral Karl Donitz, commander of the Kriegsmarine, orders emergency assessments of every submarine pen from Norway to the Bay of Biscay. The results confirm German fears. Concrete barriers that seemed impregnable against conventional bombing offer limited protection against weapons that explode from within. As word of the earthquake bomb reaches German defensive installations across occupied Europe, fortress commanders confront an terrifying reality. The Wehrmacht strategy since 1941 has relied on static fortifications, massive concrete bunkers that could withstand weeks of bombardment. The Atlantic Wall, stretching from Norway to Spain, contains 15,000 reinforced structures designed to repel invasion. Organization TOT has poured 40 million tons of concrete into 500 different types of bunkers. The entire defensive concept assumes that sufficient concrete thickness guarantees survival against air attack. The Tallboy makes that assumption obsolete overnight. June 19, 1944, brings the earthquake bomb to its most ambitious target yet, the V-weapon sites of northern France. At Wat 10, near the Belgian border, German engineers have constructed what they consider the most heavily protected installation in occupied Europe. The massive bunker, designed to manufacture and launch V-2 rockets against London, hides behind concrete walls 7 meters thick. The structure's dimensions stagger even German builders. 92 meters long, 28 meters wide, rising 35 meters above ground with foundations extending deep into bedrock. 15 Tallboys from 617 Squadron approach the Wat 10 facility at bombing altitude. The V2 production crews, working deep inside the bunker, feel secure behind their concrete barriers. The first Tallboy lands 50 meters from the bunker's northeast corner, not a direct hit, but precisely what Barnes Wallis intended. The bomb penetrates 20 meters into the chalky soil before exploding. The underground detonation creates a camouflage 100 feet across. The earth shifts, cracking the bunker's foundation along its entire length. Inside the facility, German technicians feel the structure sway like a ship in heavy seas. Concrete dust cascades from the ceiling as stress fractures spiderweb across the walls. The bunker's massive weight, previously its greatest protection, becomes a liability as the supporting soil liquefies under earthquake shock waves. Within minutes, the northeast wall develops a crack that runs from foundation to roof. The entire structure, while not destroyed, becomes too dangerous for continued V2 production. Major General Walter Dornberger, chief of the German rocket program, inspects the WW2 damage 3 days later. The Tallboy attack has not collapsed the bunker, but the building's structural integrity is permanently compromised. Sensitive rocket assembly work cannot continue in a facility where walls shift and concrete fragments fall unpredictably. Dornberger orders WW2 abandoned and V2 production relocated to underground sites deemed safer from earthquake bomb attack. The relocation delays the rocket program by crucial months, reducing the number of V2 strikes against Allied cities. The success at WW2 confirms Barnes Wallis's earthquake theory across the German defensive network. Bunker designers realize that direct hits, while devastating, represent only one threat mode. Near misses that create underground caverns pose equal danger by destabilizing foundations. This dual threat forces German engineers into an impossible position. They cannot build concrete thick enough to stop Tallboy penetration, nor can they extend foundations deep enough to avoid earthquake effects. June 24, 1944, Operation Crossbow targets the most ambitious German construction project in northern France. La Coupole, the massive V2 assembly complex near Saint-Omer. The installation represents German concrete engineering at its most sophisticated, a 55,000-ton reinforced dome 5 meters thick, designed to resist any conceivable air attack. The structure's scale dwarfs even the largest U-boat pens. Its dome, 72 meters in diameter, could accommodate a football stadium. Underground galleries extend in all directions, creating space for V2 storage, assembly, and launch operations. German engineers at La Coupole consider their creation invulnerable. The dome's curve deflects blast effects, while its massive thickness should stop any known bomb. The facility's location, partially buried in a natural hill, provides additional protection against air attack. Construction crews have worked for 18 months to create what they believe to be an impregnable fortress. The first V2 rockets are scheduled to begin launching from La Coupole within weeks. The Tallboy that targets La Coupole lands 47 meters from the dome's eastern edge, close enough to create the earthquake effect Barnes Wallis predicted. The bomb penetrates 15 meters into chalky soil before exploding with the force of an earthquake measuring 3.6 on the Richter scale. The blast wave travels through solid earth, transmitting maximum force to the dome's foundation structure. Inside La Coupole, German workers feel the massive dome flex like rubber. The concrete, stressed beyond its design limits, develops hairline cracks that spread across the inner surface. More critically, the foundation settles unevenly as the explosion's shock wave liquefies supporting soil. The dome, while intact, tilts 3 degrees from vertical, a minor angle that renders the entire facility useless for precision rocket operations. Oberst Max Wachtel, commanding officer of Flak Regiment 155W responsible for V1 and V2 operations, inspects La Coupole after the Tallboy attack. The damage appears minimal from outside. The dome remains standing. Walls show no obvious cracks, but internal measurements reveal the structure's fatal compromise. The tilt makes it impossible to align V2 rockets on their launch rails. Fuel and oxidizer lines, designed for precise tolerances, no longer connect properly to tilted launch positions. The earthquake effect has achieved what direct destruction could not, rendering the facility permanently unusable without visibly destroying it. Wachtel's report to Wehrmacht headquarters confirms German fears about the earthquake bomb concept. The Tallboy's success lies not in its explosive power. Conventional bombs carry similar destructive force, but in its ability to transmit that power through solid earth directly into target foundations. This transmission method bypasses surface protection entirely, making concrete thickness irrelevant beyond a certain point. The terror spreads to Berlin as German high command grapples with the Tallboy's implications. Every major fortification project requires reassessment. The Siegfried Line, the Atlantic Wall, submarine pens, aircraft factories, underground manufacturing facilities all become potentially vulnerable to earthquake bomb attack. Wehrmacht engineers calculate that protecting against Tallboy penetration would require concrete walls 20 meters thick, an impossibility given material and labor constraints. The psychological warfare aspect proves equally devastating. German fortress crews, previously confident in their concrete protection, now fear that any air raid might deliver earthquake bombs. The uncertainty undermines morale across defensive installations. Soldiers cannot know whether their bunker provides safety or merely creates a concrete tomb. This fear affects combat effectiveness as troops spend mental energy worrying about protection rather than fighting. July 17, 1944, brings the earthquake bomb to its greatest test. The German battleship Tirpitz, hiding in Kofjord in northern Norway. The Tirpitz represents Germany's last major naval threat to Allied Arctic convoys. At 42,500 tons displacement and armed with 8 15-inch guns, the battleship theoretically could break into the North Atlantic and devastate merchant shipping. Her presence forces the Royal Navy to maintain powerful covering forces that could otherwise support operations elsewhere. The Tirpitz poses a unique challenge for earthquake bomb tactics. Unlike static concrete bunkers, the battleship floats in water, potentially absorbing blast effects differently than land-based targets. Her armor, while formidable, measures only 12.6 inches at maximum thickness, far less than the concrete barriers Tallboys have penetrated. But the ship's mobility and location, protected by mountains and anti-aircraft defenses, complicate bombing approaches. RAF intelligence identifies the Tirpitz's vulnerability through careful analysis. The battleship, while heavily armored, relies on watertight compartments to survive battle damage. A Tallboy detonating inside the hull would create blast effects that conventional naval warfare cannot duplicate. The weapon's penetration capability should punch through deck armor before exploding within the ship's interior spaces. Alternatively, a near-miss exploding underwater would create a gas bubble effect similar to torpedo detonation but with far greater force. On September 11, 1944, 38 Lancasters of 9 and 617 squadrons begin Operation Paravane, the first Tallboy attack on the Tirpitz. The mission requires flying to Jagodnik airfield near Archangel in the Soviet Union, a staging base within range of the Norwegian target. Several bombers crash land during the complex navigation, reducing the attack force to 27 aircraft. September 15, 1944, 0955 hours. Wing Commander Willie Tate leads the Tallboy formation toward Kofjord at 14,000 feet altitude. German radar operators track the approaching aircraft, but the mountains screening the Lancasters' approach prevent early warning to the Tirpitz. The battleship's smoke screen generators activate, but too late to provide effective concealment. Tate's aircraft, leading the formation, releases its Tallboy directly over the Tirpitz's forward section. The 12,000-pound weapon plunges toward the battleship at terminal velocity, spinning for accuracy as Barnes Wallis designed. 37 seconds after release, the Tallboy strikes the Tirpitz's forecastle and punches completely through the armored deck, hull plating, and keel before exploding in the fjord bottom beneath the ship. The underwater explosion creates effects no naval designer anticipated. The Tallboy's 5,200 pounds of torpex generate a gas bubble 200 feet in diameter, lifting the Tirpitz's 42,500-ton hull partially out of the water before the bubble collapses. The shock wave, transmitted through water more efficiently than through air, buckles the battleship's hull plates along 120 feet of her length. Seawater floods the forward compartments faster than damage control parties can respond. Aboard the Tirpitz, Captain Zur C. Robert Weber feels his battleship shudder like a living thing in mortal pain. The explosion beneath the keel creates vibrations that travel through the ship's steel framework, cracking welds and loosening rivets throughout the structure. Water pours through sprung plates in the forward sections, creating a list that grows worse despite counterflooding efforts. The ship's trim changes drastically as 2,000 tons of seawater fill compartments never designed to carry such weight. Weber's damage control reports confirm the Tallboy's devastating effectiveness against naval targets. The battleship's forward machinery spaces have flooded, limiting maximum speed to 8 knots. Fire control systems, jarred by the explosion's shockwaves, no longer provide accurate gun laying. Most critically, the hull damage cannot be repaired away from a major shipyard, and no German port remains accessible to the damaged vessel. Admiral Karl Donitz receives Weber's report with growing dismay. The Tirpitz, Germany's last operational battleship and a cornerstone of defensive strategy, has been rendered unfit for combat by a single bomb. The weapon that struck her represents a new category of threat that naval armor cannot counter. Conventional naval gunfire, torpedo attack, even aerial bombing with standard weapons had failed to disable the Tirpitz decisively. The earthquake bomb succeeded where all previous attacks had failed. Donitz faces an impossible decision. The Tirpitz cannot reach a shipyard capable of repairing her damage. Soviet forces advancing toward Kofjord threaten to overrun the anchorage within months. The battleship's combat effectiveness has been eliminated, but she retains value as a floating artillery battery. Donitz orders the Tirpitz towed to Tromsø, farther south in Norway, where she can defend the harbor while undergoing temporary repairs. The decision to move the Tirpitz proves fatal. Tromsø lies within range of RAF bombers operating from Scotland, eliminating the protective distance that had shielded the battleship in Kofjord. German engineers, unaware of this vulnerability, focus on sandbank construction beneath the ship's hull protection against conventional torpedo attack but useless against earthquake bombs dropped from above. October 29, 1944, Operation Aviate brings 32 Lancasters with Tallboys to Tromsø. Cloud cover obscures the target, preventing accurate bombing. The aircraft release their weapons on estimated positions, but no direct hits occur on the Tirpitz. One near miss damages the port rudder and causes minor flooding, but the battleship remains afloat and operational as a harbor defense battery. The unsuccessful attack deceives German defenders into believing they can protect the Tirpitz through improved positioning and anti-aircraft defense. Additional flak ships arrive in Tromsø Fjord. Shore-based gun batteries increase their ammunition supplies. Luftwaffe fighters base at nearby Bardufoss airfield, ready to intercept future bombing attempts. The Germans prepare for conventional air attack, not understanding that earthquake bombs require different defensive measures. November 12, 1944, 0930 hours. 31 Lancasters of 9 and 617 squadrons approach Tromsø in clear weather conditions. The Tirpitz lies anchored in shallow water, her crew confident in the sandbank protection German engineers have constructed. Anti-aircraft guns open fire at 13-mile range, but the Lancasters maintain formation and bombing approach. At 0938 hours, the first Tallboy strikes the Tirpitz between her forward turrets, penetrating the armored deck and exploding deep inside the hull. The detonation occurs within the ship's vitals boiler rooms, magazine spaces, machinery compartments. Unlike the Kofjord attack where the bomb exploded underwater, this direct hit unleashes the Tallboy's full destructive force inside the battleship structure. The explosion vaporizes everything within a 100-foot radius inside the hull. Bulkheads designed to contain torpedo damage cannot withstand blast effects generated by 5,200 pounds of torpex detonating in an enclosed space. The ship's internal structure frames, decking, machinery foundations disintegrates under pressures no naval architect envisioned. A second Tallboy strikes amidships between the aircraft catapult and funnel, creating another internal explosion that completes the battleship's destruction. The combined blast effects destroy the Tirpitz's structural integrity along her entire length. Water floods through massive hull breaches faster than any pumping system could manage. Captain Zur C. Weber, observing from the bridge, watches his battleship die beneath him. The port list increases rapidly as thousands of tons of water pour through breached compartments. At 0948 hours, Weber orders abandon ship, as the list reaches 30 degrees. The Tirpitz continues rolling to port, reaching 60 degrees by 0950 hours. At 0958 hours, an internal explosion rocks C turret as the magazine detonates. The turret roof and rotating structure blast 25 meters into the air, crushing swimmers in the water below. The explosion destroys the ship's remaining stability, and the Tirpitz rolls completely over, trapping more than 900 crew members inside the capsized hull. The Tirpitz's destruction represents the earthquake bomb's greatest victory. Germany's last battleship, protected by the most sophisticated naval armor ever built, succumbed to 2 direct hits from weapons that did not exist 3 years earlier. The psychological impact resonates throughout the Kriegsmarine as officers realize that no ship, regardless of armor thickness, can survive earthquake bomb attack. Admiral Donitz's reaction to the Tirpitz's loss reveals the terror that Barnes Wallis's weapon has instilled in German naval thinking. The battleship represented more than firepower; she symbolized German naval engineering supremacy and the possibility of challenging Allied control of sea lanes. Her destruction by earthquake bombs demonstrates that traditional naval protection concepts no longer apply in modern warfare. The ripple effects of the Tirpitz's sinking extend far beyond naval operations. German strategic planning had allocated enormous resources to protecting and supporting the battleship. Coastal artillery, fighter aircraft, repair facilities, fuel supplies, and personnel all dedicated to keeping the Tirpitz operational as a fleet in being. Her destruction by 2 bombs releases these resources for other purposes, but too late to affect the war's outcome. Major Heinrich Oehler, commanding officer of Group 3, Jagdgeschwader 5, faces court-martial for his failure to provide air cover during the final Tirpitz attack. The Luftwaffe fighters never took off from Bardufoss, despite frantic radio calls for air cover from the battleship. Oehler's threatened death sentence reflects German high command frustration with their inability to counter earthquake bomb attacks effectively. The court-martial proceedings reveal the communication breakdown between German services. Naval requests for air cover went unanswered because Luftwaffe commanders had not been informed of the Tirpitz's relocation to Tromsø 2 weeks earlier. The failure represents broader German difficulties in coordinating defense against precision bombing attacks that require rapid response. Oehler's eventual sentence 3 years in prison, reduced to 1 month served, and his subsequent assignment to an Me-262 jet fighter squadron suggests German recognition that the Luftwaffe's failure resulted from systemic problems rather than individual negligence. The earthquake bomb attacks succeeded partly because German defensive coordination could not match the speed and precision of RAF special bombing operations. As news of the Tirpitz's destruction spreads through German defensive installations, fortress commanders confront their vulnerability to similar attacks. The battleship's 14-inch armor proved useless against earthquake bombs that exploded from within. Concrete bunkers, while thicker than naval armor, face the same penetration threat from weapons designed to punch through any barrier before exploding. The terror extends beyond immediate military concerns into German civilian morale. The Tirpitz represented invincible strength to German propaganda, a symbol of technological superiority that would protect the fatherland from Allied invasion. Her sudden destruction by British super bombs contradicts Nazi assurances about German defensive capability. Citizens begin questioning whether their concrete air raid shelters can protect them if the British possess weapons that destroy battleships with single hits. December 1944 through April 1945 brings the earthquake bomb campaign to German submarine pens, the most heavily protected installations in occupied Europe. These massive concrete structures, built to withstand years of bombardment, represent the ultimate test of Tallboy effectiveness against static fortifications. The pens house Germany's U-boat fleet, the last German naval force capable of challenging Allied supremacy in the Atlantic. The submarine pen at Bergen, Norway, presents typical construction. Reinforced concrete walls 5 meters thick, with a roof 3.5 meters thick designed to deflect any bomb in the Allied arsenal. The structure's dimensions stagger even German engineers familiar with large-scale construction. 400 meters long, 97 meters wide, with internal spaces capable of servicing a dozen U-boats simultaneously. German naval architects consider the facility absolutely impregnable. December 12, 1944. 32 Lancasters of 9 and 617 squadrons attack Bergen Harbor with Tallboys. 3 bombs penetrate the submarine pen's 3.5-meter roof and explode inside, destroying workshops, offices, fuel storage, and ammunition magazines. The internal explosions prove more devastating than external detonations would have been. The concrete roof that protected against conventional bombing becomes a containment barrier that focuses earthquake bomb effects inward. U-boat crews sheltering inside the pens experienced terror beyond anything they faced at sea. The explosions inside the confined space create blast effects that liquefy human bodies and turn concrete fragments into deadly shrapnel. Submarines under repair suffer damage that makes them unseaworthy. Critical equipment periscopes, torpedo tubes, diesel engines, electrical systems cannot withstand the shockwaves generated by Torpex explosions in enclosed spaces. Captain zur See Hans Rudolf Rosing, commanding officer of U-boat operations in Bergen, surveys the destruction with growing horror. The submarine pen, considered the safest location in occupied Norway, has become a death trap. 3 direct hits from earthquake bombs have rendered the facility unusable for submarine operations. The U-boats that survived the attack require extensive repairs at facilities that no longer exist. The Bergen attack pattern repeats across German submarine installations. Brest receives 6 direct Tallboy hits that penetrate its concrete roof and devastate interior facilities. Saint-Nazaire, protected by 8-meter reinforced concrete, suffers roof penetration and internal destruction. Imoiden and Portershaven endure similar attacks, with Tallboys punching through barriers previously considered bomb-proof. The submarine pen attacks prove that concrete thickness alone cannot protect against earthquake bombs. The Tallboy's penetration capability exceeds any practical concrete barrier thickness. German engineers calculate that stopping Tallboy penetration would require concrete roofs 15 meters thick, an impossibility given material shortages and construction time constraints. At Hamburg, the Valentin submarine pen represents German concrete engineering at its most ambitious. 4.5-meter thick walls, with the eastern section reinforced to 7 meters, designed to be the largest fortified U-boat facility in Germany. The structure scale dwarfs previous construction, 426 meters long, 97 meters wide, covering over 35,000 square meters. Forced laborers have worked for 2 years to create what German engineers believe will be invulnerable to any air attack. March 27, 1945, brings 20 Lancasters with 13 Grand Slam bombs and 7 Tallboys to attack Valentin. The Grand Slam, Barnes Wallis's ultimate earthquake weapon at 22,000 pounds, represents the logical evolution of Tallboy technology. 2 Grand Slams penetrate halfway through Valentin's 4.5-meter western wall before exploding, breaking through the remaining concrete and collapsing the roof onto workers below. The Valentin attack demonstrates earthquake bomb effectiveness against the heaviest fortifications Germany can build. Even 7-meter concrete cannot provide absolute protection. The facility, while not completely destroyed, suffers structural damage that makes U-boat assembly impossible. The shifting foundations and cracked walls cannot support precision manufacturing operations required for submarine construction. Oberbarett Franz Xaver Dorsch, chief engineer of Organisation Tot, inspects the Valentin damage and concludes that concrete fortification has reached its practical limits. Further increases in wall thickness provide diminishing returns against earthquake bomb penetration. The resource allocation required for truly bomb-proof construction exceeds Germany's remaining industrial capacity. The psychological impact of submarine pen destruction resonates throughout the Kriegsmarine. U-boat crews, accustomed to the safety of concrete shelters between patrols, face the reality that no shore installation provides security against earthquake bomb attack. The pens that protected submarines from Allied bombing now become potential tombs if British bombers arrive with Tallboys. As the earthquake bomb campaign reaches its climax in early 1945, German defensive strategy collapses under the weight of strategic impossibility. Every major fortification requires protection against weapons that can penetrate any practical concrete thickness. The resources needed for such protection exceed Germany's industrial capacity even if materials and labor were unlimited. General Heinrich Gottfried von Weidinghoff-Scheel, commanding Army Group C in Italy, receives reports that perfectly illustrate German defensive helplessness. Italian concrete fortifications, built to the same standards as Atlantic Wall installations, offer no protection against earthquake bombs. Allied forces advancing through Italy face minimal resistance from fortified positions that German engineers considered impregnable months earlier. The terror spreads through German military psychology as officers realize their defensive doctrine has become obsolete. Static fortification, the cornerstone of Wehrmacht defensive strategy since 1941, cannot protect against weapons that explode from within concrete barriers. Mobile defense offers the only viable alternative, but German forces lack the fuel, equipment, and air cover necessary for effective maneuver warfare. Meanwhile, across the Pacific, Japanese military engineers observe the Tallboy's European success with growing alarm. Intelligence reports from Germany describe earthquake bombs that penetrate concrete barriers and destroy fortifications from within. Japanese defensive planning on Iwo Jima, Okinawa, and the home islands relies heavily on underground installations that might prove vulnerable to similar weapons. Lieutenant General Tadamaki Kurabayashi, commanding Japanese forces on Iwo Jima, reviews American intelligence estimates and realizes that conventional concrete fortifications cannot protect against earthquake bomb attack. His defensive strategy shifts toward deep cave systems carved into volcanic rock positions that might survive underground explosions better than surface bunkers. Kurabayashi's engineers exploit Iwo Jima's unique geology to create defensive positions 18 kilometers deep, using volcanic ash that hardens into superior concrete when mixed with cement. The tunnel network connects multiple defensive levels, with ventilation systems designed to survive blast effects and debris blocking. Japanese military engineers believe their cave systems will prove more resilient than European concrete bunkers. American intelligence, monitoring Japanese defensive preparations, identifies the need for specialized weapons against cave fortifications. The T-10 bomb, an American version of the Tallboy modified with standard United States components, enters development specifically for Pacific theater operations. Plans call for B-29 superfortresses to drop T-10s against Japanese cave systems on Iwo Jima, Okinawa, and the home islands. The T-10 development program reveals American understanding of earthquake bomb principles learned from British Tallboy success. American engineers calculate that Japanese cave systems, while deeper than European bunkers, remain vulnerable to underground explosions that collapse supporting rock formations. The T-10's design prioritizes penetration through volcanic rock rather than concrete, with fusing adjusted for subsurface detonation in cave networks. Major General Curtis LeMay, commanding the XXI Bomber Command, reviews targeting plans for Japanese fortifications and concludes that conventional incendiary bombing cannot neutralize cave systems effectively. The T-10 program represents the only viable option for destroying underground defensive positions before American amphibious assaults. LeMay allocates B-29 squadrons for earthquake bomb training, preparing for operations that will soften Japanese defenses using Barnes Wallis's penetration principles. Japanese defensive planners, unaware of specific American earthquake bomb development, nevertheless understand the threat that such weapons would pose to their cave systems. Intelligence estimates suggest that underground explosions could collapse tunnel networks regardless of depth or structural reinforcement. This threat forces Japanese engineers into the same impossible position faced by German bunker builders. No practical fortification can provide absolute protection against earthquake bomb attack. The psychological pressure affects Japanese defensive planning as commanders realize their underground fortresses might become death traps if American bombers arrive with earthquake weapons. Cave systems designed to provide safety could become mass graves if penetrating bombs exploded within the tunnel networks. This uncertainty undermines Japanese confidence in their defensive preparations. Emperor Hirohito, reviewing defensive plans for the home islands, questions whether Japanese fortifications can withstand American earthquake bomb attack. Military advisors acknowledge that no defensive position offers absolute security against weapons that explode underground. The admission represents a fundamental shift in Japanese strategic thinking from confident defense to acceptance of inevitable vulnerability. The terror reaches its ultimate expression in Japanese planning for Operation Ketsugo, the defense of the home islands against American invasion. Japanese engineers understand that their concrete bunkers, underground factories, and cave networks cannot protect against earthquake bomb attack. Defense must rely on dispersed positions, mobile tactics, and acceptance of enormous casualties rather than fortress-style resistance. As the Pacific War reaches its climax in summer 1945, American T-10 bombs await deployment against Japanese cave systems. The weapons, designed to collapse underground fortifications through earthquake effects, represent the logical evolution of Barnes Wallis's penetration theory adapted for Pacific theater geology. B-29 crews train for precision attacks on Japanese defensive positions using 12,000-pound bombs that will punch through volcanic rock before exploding deep underground. The atomic bombs dropped on Hiroshima and Nagasaki render the T-10 program unnecessary. Japan's surrender on August 15, 1945, cancels planned earthquake bomb attacks on cave systems that might have caused enormous Japanese casualties. The T-10 weapons enter storage, later used during the Korean War against bridges and dams but never tested against the underground fortifications for which they were designed. In Italy, the earthquake bomb campaign produces its own unique terror among defenders and civilians alike. Allied forces advancing through the peninsula encounter concrete fortifications that offer no protection against Tallboy attack. German defensive positions, built to Italian engineering standards, prove as vulnerable as Atlantic Wall installations to penetrating bombs that explode from within. Pope Pius XII, surveying bomb damage in Rome's San Lorenzo district, witnesses the terror that earthquake weapons could inflict on civilian populations. The papal apartments vibrate as Allied bombers pass overhead, carrying weapons capable of penetrating any shelter. Vatican radio broadcasts emphasize the indiscriminate nature of modern warfare, where even neutral institutions cannot guarantee safety against penetrating bombs. Italian civilians, caught between German occupation and Allied liberation, experience the terror of modern bombing campaigns that make concrete shelters useless. Air raid shelters built to protect against conventional bombs offer no security against weapons that explode underground. Families huddle in basements and tunnels, knowing that concrete thickness provides illusory protection against earthquake bombs. The psychological warfare aspect of earthquake bomb deployment extends beyond immediate military targets to affect civilian morale throughout occupied Europe. Populations that had felt secure behind concrete barriers discover that no shelter offers absolute protection. This realization contributes to the collapse of civilian confidence in German defensive capability and accelerates the process of surrender. German propaganda attempts to counter the earthquake bomb threat by claiming that British terror weapons violate international law and prove Allied barbarism. But the propaganda fails to address the fundamental problem. Germany cannot build fortifications thick enough to protect against Tallboy penetration. The weapons represent a technological advancement that makes existing defensive doctrine obsolete. Dr. Joseph Goebbels, Reich Minister of Propaganda, struggles to explain how British earthquake bombs destroy installations that German engineering promised were impregnable. The propaganda narratives that sustained German morale, superior technology, impenetrable fortresses, inevitable victory collapse under the evidence of Tallboy effectiveness. Citizens who trusted in concrete protection lose faith in official assurances about defensive capability. The terror reaches into German scientific circles as physicists and engineers realize the implications of earthquake bomb success. Professor Werner Heisenberg, leading German atomic research, understands that British weapons represent a fundamental breakthrough in explosive delivery rather than explosive power. The achievement lies not in creating larger bombs, but in ensuring that explosions occur at precisely the right location for maximum structural damage. German atomic researchers, struggling with uranium enrichment and reactor design, recognize that they have been pursuing the wrong approach to superweapons. While they focused on nuclear explosives, British scientists developed delivery systems that make conventional explosives far more effective. The earthquake bomb concept requires no exotic materials or complex physics, only precise engineering and manufacturing capability that Germany can no longer match. Albert Speer, Reich Minister for Armaments and War Production, reviews damage reports from earthquake bomb attacks and calculates the economic impact of Tallboy operations. Each successful attack eliminates industrial facilities that required months or years to construct. The British investment in earthquake bomb development, perhaps thousands of man-hours and moderate material costs, generates returns measured in destroyed factories, disabled transportation networks, and diverted defensive resources. Speer's analysis reveals the economic leverage that earthquake bombs provide to Allied forces. German defensive construction consumes enormous resources while remaining vulnerable to weapons that cost relatively little to produce and deploy. This economic imbalance makes German fortification strategy unsustainable even if materials and labor were unlimited. The psychological pressure extends to German military leadership as generals realize their strategic doctrine has been rendered obsolete by technological change. Field Marshal Gerd von Rundstedt, formerly confident in Atlantic wall defenses, acknowledges privately that concrete fortifications cannot protect against earthquake bomb attack. The admission represents a fundamental shift in German strategic thinking from fortress warfare to mobile defense concepts that Germany lacks the resources to implement effectively. General Heinz Guderian, Inspector General of Armored Troops, reviews battlefield reports and concludes that static defense has become impossible against enemies possessing earthquake bombs. Mobile warfare offers the only viable alternative, but German forces lack the fuel, air cover, and equipment necessary for effective maneuver operations. The strategic situation becomes hopeless as technological change eliminates defensive options while offensive capability remains inadequate. The terror culminates in German civilian populations as earthquake bomb attacks demonstrate that no shelter provides absolute security. Families that had trusted in concrete air raid shelters discover that penetrating bombs can destroy any protection. This realization contributes to the collapse of civilian morale and the acceleration of German surrender. As Allied forces advance across Europe in spring 1945, they encounter German defensive positions abandoned not because of direct attack but because defenders understood their positions offered no protection against earthquake bomb assault. The psychological impact of Tallboy operations proves as important as their physical destruction. German forces lose confidence in their defensive capability and retreat before battles begin. The earthquake bomb campaign reaches its conclusion with Germany's surrender on May 8, 1945. In total, 854 Tallboys and 41 Grand Slams have been deployed against targets throughout occupied Europe. The weapons achieved strategic effects far beyond their numbers by demonstrating that no fortification could provide absolute protection against penetrating bombs that exploded from within concrete barriers. Barnes Wallis's theoretical concept, sketched on drafting tables in 1941, has evolved into the weapon that renders fortress warfare obsolete. The earthquake bomb principle, underground explosions that transmit force through solid earth rather than dissipating through air, represents a fundamental advancement in military technology that changes the mathematics of destruction forever. The terror that earthquake bombs instilled in German defensive thinking spreads throughout military establishments worldwide as nations realize that static fortification cannot protect against weapons designed to penetrate and explode from within protective barriers. The successful deployment of Tallboy and Grand Slam bombs establishes principles that influence bunker-busting weapon development into the modern era. German engineers, captured after the war, provide technical details that confirm Allied estimates of earthquake bomb effectiveness. Concrete barriers that seemed impregnable proved vulnerable to weapons that generated underground explosions. The psychological impact of this vulnerability proved as important as the physical destruction, undermining confidence in defensive capability and accelerating the collapse of German resistance. Japanese military leaders, studying European earthquake bomb effects after their own surrender, acknowledged that their cave system defenses would have proven vulnerable to similar weapons. The T-10 bombs designed for Pacific operations might have collapsed tunnel networks and eliminated Japanese defensive positions without requiring direct hits on cave entrances. Italian military engineers, examining bomb damage after the war, conclude that their concrete fortifications offered no protection against earthquake bomb attack. The weapons demonstrated that technological advancement could render existing defensive doctrine obsolete overnight, forcing military planners to reconsider fundamental assumptions about fortification and protection. The legacy of earthquake bomb development extends far beyond World War II as military establishments worldwide incorporate Barnes Wallis's penetration principles into modern bunker-busting weapon design. The concept that bombs should explode underground rather than on surface targets becomes standard doctrine for attacking hardened installations. Modern weapons like the GBU-28 and GBU-57 massive ordnance penetrator trace their development directly to Tallboy principles established during World War II. These weapons use similar concepts: hardened casings, aerodynamic design, delayed fusing to achieve underground explosions that destroy targets from within protective barriers. The terror that earthquake bombs created in German, Japanese, and Italian defensive planning demonstrates how technological advancement can shift strategic balance overnight. Fortifications that required years to build and enormous resources to maintain became vulnerable to weapons that cost relatively little to develop and deploy. The psychological warfare aspect of earthquake bomb deployment proved as important as the physical destruction. Defenders who lost confidence in their protective barriers became vulnerable to defeat before battles began. This psychological leverage multiplied the strategic effect of relatively few weapons deployed against carefully selected targets. The earthquake bomb campaign of 1944-1945 represents a revolution in military technology that rendered traditional fortress warfare obsolete. Barnes Wallis's concept bombs that penetrate underground before exploding created weapons that transmitted destructive force through solid earth rather than dissipating through air. This fundamental change in explosive delivery made concrete thickness irrelevant beyond a certain point, terrorizing defenders who had trusted in barrier protection. The terror spread from German bunkers to Japanese cave systems to Italian fortifications as military engineers realized that no practical fortification could provide absolute security against earthquake bomb attack. This realization contributed to the collapse of Axis defensive confidence and hastened the end of World War II. The legacy continues in modern military technology as bunker-busting weapons employ principles established by the Tallboy and Grand Slam bombs. The terror that Barnes Wallis's earthquake weapons created in 1944 resonates through contemporary military planning as nations understand that technological advancement can render existing defenses obsolete without warning. In the final analysis, the earthquake bomb campaign achieved victory not through superior firepower but through superior understanding of how force transmits through solid matter. The terror it created in Axis defensive thinking demonstrates that psychological warfare often proves more effective than physical destruction in determining strategic outcomes. The 12,000-pound Tallboy and 22,000-pound Grand Slam represented more than large bombs. They embodied a fundamental shift in military thinking from quantity to precision, from surface effects to subsurface destruction, from conventional tactics to revolutionary technology that made fortress warfare obsolete forever. The terror was complete, the fortresses crumbled, and the earthquake bombs had changed warfare forever.